Imagine for a moment that the universe we experience, forward and back, left and right, up and down, is only the visible face of something far stranger. Physicists have long suspected that what we call three dimensions might be accompanied by others so tiny or hidden that we never notice them. In one picture, those extra directions are curled up, impossibly small. In another, our whole cosmos is a membrane, a thin sheet floating in a higher dimensional space. Either way, those hidden layers could be shaping everything we observe, even if we cannot directly see them. Now, consider a radical possibility. What if an advanced algorithm, fed with the deepest images from the James Webb Space Telescope, pulled a faint pattern from the noise, an imprint that points to an extra layer of space? Not science fiction, but a precise, testable scientific hypothesis. Tonight we trace a clear path from raw telescope pixels to a claim about dimensions beyond our own, and we do it the right way, transparent, repeatable, and brutally skeptical. The starting point is gravitational lensing. Massive galaxies bend light from distant sources into arcs and rings, perfect laboratories for gravity. Take an Einstein ring, model the mass that produced it, subtract everything you know about stars, gas, and dark matter, and sometimes you are left with tiny leftovers. Residual ripples in the image that our current physics can't immediately explain. Those leftovers are often dismissed as noise or instrument quirks. But what if, when you collect those residuals across hundreds or thousands of lenses, a consistent signal emerges, a statistical rhythm no single image could reveal on its own? Call this approach residual cosmography. Rather than hunting for one spectacular anomaly, it searches for a coherent statistical signature distributed across the entire population of lenses. Think of a vinyl record. The music is the strong, visible signal, the galaxies and arcs we understand. But the tiny scratches on the record create a subtle hiss. Run a powerful enough analysis over all the grooves and the hiss reveals a repeated rhythm. That rhythm, if it exists, may match exactly what a braneworld leakage model predicts. A small but specific bump in the power spectrum of residuals that scales with lens mass and distance in precise ways. Detecting that rhythm is computationally brutal. The James Webb Archive already contains deep fields studded with exquisite Einstein rings. The European Space Agency's Euclid mission complements Webb by sweeping an enormous area of sky and cataloging tens of thousands of lenses. Together, they create a dataset of staggering size. Sorting through millions of potential lens candidates to find the faintest, most consistent residual patterns is beyond the comfortable reach of traditional methods. Enter quantum-assisted analysis. Quantum processors like Google's Willow don't see dimensions. They don't scan the sky with new eyes. What they do exceptionally well is extract high-dimensional patterns from enormous datasets, highlighting candidate anomalies for rigorous classical follow-up. In practice, quantum kernel methods perform aggressive dimensionality reduction, compressing the essential structure of thousands of lens images into a compact mathematical form where subtle, consistent features stand out. The quantum chip acts as a highly efficient pattern detector, flagging targets that classical triage would likely miss. But quantum assistance is only the beginning. Scientific integrity requires open data, pre-registered tests, and exhaustive attempts to break the signal. The full analysis must use publicly available web data from the MAST archive and Euclid data from ESA repositories. The code, the random seeds used for synthetic tests, the exact statistical metrics, everything goes on GitHub before a single unblind result is revealed. That prevents the temptation to cherry-pick and ensures that independent groups can reproduce, validate, or falsify the finding. What does the pipeline actually do? Start with the cleanest Einstein rings in Webb's deepest fields, those near-perfect cosmic donuts that minimize modeling ambiguities. For each ring, build an ultra-precise lens model that includes stars, gas, dust, and dark matter substructure. Subtract that model from the image and map what remains, the residual image. Then translate that residue into a power spectrum, a breakdown of how much texture exists at every angular scale, like analyzing the bass and treble of a piece of music. Look for a distinctive bump at a particular scale that appears more often than chance would allow. The hypothesis is simple and falsifiable. First, standard cosmology, cold dark matter, baryons, and known physics predicts residuals at a certain level and with a particular shape. Braneworld models that allow a tiny leakage of gravity into an extraspatial direction predict an additional, calculable contribution. A distinct bump in the power spectrum whose amplitude and position scale in specific ways with the lens mass and the cosmic distance between lens and source. The test is to see which model wins on objective statistical grounds. This is where strict cross-field and cross-mission consistency matter. If the signature appears only in one deep Webb field and disappears in others, the hypothesis collapses. Similarly, the Euclid survey is the ultimate cross-check. Webb probes extremely deep, very small patches of sky with exquisite angular resolution and spectroscopic diagnostics. Euclid trades depth for breadth and will deliver vast statistical power. Lensing systems observed independently by both telescopes must show the same residual pattern if the effect is real and not a telescope idiosyncrasy. To avoid false positives, the analysis must be armored with blinding, synthetic injections, and hostile null tests. Researchers blind the lens list and scoring rules so selection bias cannot creep in. They inject artificial subhalos, small clumps of dark matter, into raw images at controlled strengths to verify that the pipeline can recover known signals. They deliberately manipulate point spread functions and dither patterns. Instrumental signatures created this way will move with the telescope's behavior, whereas a genuine cosmic residual is anchored to its position on the sky. A rigorous statistical framework is essential. Each model's performance gets evaluated with Bayes factors, the suspiciousness statistic, and other quantitative tools that penalize overfitting. Bayes factors compare how well each model explains the data while disfavoring unnecessary complexity, favoring parsimonious explanations that capture real structure. The suspiciousness statistic quantifies tension between datasets and models, helping catch cases where an apparent improvement is simply fitting random noise. Together, these methods drive objectivity. Numbers speak louder than intuition. The scientific duel is direct and ruthless. On one side are the established champions, standard cosmology, cold dark matter, and variants like self-interacting dark matter that already explain many cosmic structures. On the other side sit braneworld models that add a precise, testable leakage term to Einstein's equations. Both camps apply identical analysis pipelines to identical datasets. A decisive score, Bayesian evidence that significantly favors one model over the other, decides which explanation is more credible. If the braneworld model consistently wins across independent fields and instruments, the claim moves from intriguing to worthy of intense scrutiny. Why bring quantum chips into a problem physicists have attacked for decades? The answer is scale. Euclid will identify well over 100,000 gravitational lenses during its mission. Running exhaustive lens modeling and residual power spectrum analysis on every candidate using conventional resources would take many human lifetimes. Quantum kernel methods don't replace classical science. They speed the search for needles in a statistical haystack, prioritizing candidates without introducing bias. Every flagged candidate still undergoes the same rigorous classical verification. Could ordinary astrophysical processes masquerade as the extra-dimensional signature? Stars, gas, and dust are complicated, and they can create subtle patterns in lensing arcs. This is why null tests are designed to be exhaustive. The analysis explicitly models stellar populations, gas dynamics, and dusty structures. Synthetic tests inject these astrophysical complexities at controlled levels to see whether they can reproduce the apparent bump in the residual power spectrum. If dust or stellar clumps were responsible, the null tests will show that. If they are not, the effect must have a different origin. What if Webb and Euclid disagree? Then the hypothesis stalls. Cross-mission inconsistency is fatal for a claim of new physics. Different instruments have different systematic behaviors. Resolving contradictions reveals whether issues lie in instrument modeling, sample selection, or subtle data reduction choices. No legitimate scientific claim advances while two independent telescopes give contradictory answers about identical sky regions. Scientific integrity demands transparency at every step. Before a single unblind result, the research team must pre-register the complete lens sample selection criteria, scoring metrics, and statistical tests. The entire codebase freezes before unblinding. No tweaking algorithms after seeing the outcome, no adjusting parameters to nudge marginal signals toward significance. The analysis runs once exactly as documented with independent witnesses verifying the process. External teams are invited to clone and run the experiment independently. Only when multiple groups reach the same conclusion does the result gain real credibility. Beyond the procedure, consider the implications. An extra spatial dimension would not merely rewrite physics textbooks. It would ripple into every technology that depends on precise models of gravity. Navigation systems, atomic clocks, deep space trajectory planning, quantum sensors, each relies on our current understanding of spacetime geometry. Even a microscopic leakage of gravity into another dimension could require recalibrating instruments and rethinking mission architectures. Galaxy formation models would change, potentially altering estimates for how quickly stars, planets, and habitable environments can arise in the universe. The search scales naturally. Move beyond a handful of gorgeous Einstein rings and analyze the tens of thousands of lenses Euclid will deliver. Each lens system is categorized by lens mass, lens redshift, and source redshift, creating buckets of similar systems for comparative tests. A genuine extra-dimensional effect should shift the power spectrum bump in precise, mathematically predicted ways across those buckets. This is the ultimate knockout test. Population statistics that reveal not one exceptional case but a pattern that matches theoretical expectations across thousands of independent systems. Citizen science provides a complementary verification layer. Curate a set of a few thousand arcs containing a mixture of real images and synthetic injections and release them through a Zooniverse-style platform. Volunteers classify anomalies blind to which images are manipulated. When the crowd consensus statistically matches algorithmic flags, the automated pipeline gains extraordinary credibility. Citizen participation does not replace rigorous statistics, but it strengthens public verification and helps detect unexpected failure modes. Let's return to intuition. Picture our three-dimensional world as a long corridor. Alongside it runs a hidden hallway that most objects cannot cross. Light and ordinary particles bounce along our corridor. They do not pass through the wall into the hidden space. Gravity, however, might be different. In some theoretical models, it can leak into that parallel hallway, taking shortcuts and slightly changing how space curves around mass. The tiny deflection this produces could be visible as a specific pattern in the residuals after all conventional lensing physics is subtracted. This program defines clear gates for acceptance. Gate 1. The distinctive residual bump must repeat consistently across independent telescope fields. Gate 2. A braneworld leakage model must outperform standard cosmology in head-to-head, preregistered statistical comparisons, gaining higher Bayesian evidence and lower tension metrics by a statistically significant margin. Gate 3. The effect must scale with mass and distance exactly as the mathematical model predicts. Fail any gate and the hypothesis needs revision or rejection. Pass all three and the claim advances to even more stringent verification. To appreciate how delicate these measurements are, imagine forensic work where the primary evidence is loud and visible, but the decisive clue is a hair-thin pattern repeated across hundreds of scenes. That metaphor captures why ensemble statistics matter more than singular spectacle. The analysis must control for many pernicious effects: detector quirks, cosmic rays, thermal flexure, and calibration drifts. Fortunately, many instrument artifacts betray themselves with telltale behaviors. Observatories use dithered exposures, small, planned offsets between frames, so bad pixels and detector blemishes fall in different places. If a suspicious feature shifts with how you reproject the dithered exposures, it is almost certainly instrumental. A true cosmic residual will persist regardless of how you shuffle exposures. Spectral information strengthens this test. Webb's infrared imagers and spectrographs separate light by wavelength, letting analysts distinguish which photons originate in the lens galaxy and which from the background source. That color and redshift information helps pin down the lensing geometry and reduces modeling uncertainty. Euclid's wide-field visible surveys supply complementary photometry across enormous sky areas, improving source identification in a way that is orthogonal to Webb's deep spectroscopy. Statistical rigor is non-negotiable. Bayes factors weigh how well competing models explain the same data while penalizing unnecessary complexity, the scientific equivalent of preferring the simplest story that fits the facts. Suspiciousness and related tension metrics help spot overfitting and dataset inconsistency. Together, these methods ensure that a nominal improvement in fit is not merely a clever rewrite of noise. Synthetic injections serve as stress tests. Controlled subhalos, tiny artificial mass clumps, are added to raw images at known positions and strengths. If the pipeline finds these implants with the expected sensitivity and false positive rate, analysts can trust its performance on unknown data. If not, the pipeline needs refinement before any claim about real anomalies can be credible. This strategy encourages cultural reform in cosmology. Pre-registration, open replication, and public audit trails. These practices, borrowed from fields that have faced reproducibility crises, reduce the risk of spuriously promoted discoveries. When results are transparent from the outset, independent teams can validate findings, replicate runs on different hardware, and expose fragile dependencies. There is an educational payoff as well. Public repositories with curated teaching datasets let students and citizen scientists practice the analysis chain. A Zooniverse-style interface can present volunteers with a mix of real and injected images. When crowd classifications statistically agree with algorithmic flags, blind to which images are manipulations, confidence in the automated pipeline rises. Citizen science becomes a complementary verification layer, not a substitute for rigorous statistics. Philosophically, confirming an extraspatial dimension would alter basic assumptions about locality and causation. If gravity can slip into a hidden corridor, information about mass distributions could travel along unexpected shortcuts, demanding new theoretical work connecting quantum information and gravitational dynamics. Even if the investigation yields a null result, the tightened constraints provide powerful guidance to theorists, ruling out broad classes of speculative models. Technically, quantum kernel methods are not mystical. They are advanced pattern recognition tools that must be validated against classical baselines. Any candidate highlighted by quantum triage requires classical follow-up, detailed lens modeling, spectral checks, and instrument simulations. Interpretability matters. Researchers must show which features the quantum representation emphasized and why. What would a convincing announcement look like? Picture a concise paper with 3 central figures. The residual bump reproduced across multiple independent web fields, a model comparison plot showing consistently higher Bayesian evidence for the braneworld leakage model, and a scaling plot where the effect moves with lens mass and distance exactly as predicted by theory. Accompanying this paper would be a public GitHub repository containing frozen code, pre-registered tests, and all random seeds used in the analysis so independent teams can reproduce every numerical step. Remember also the power of a robust null result. Demonstrating that no extra-dimensional signature exists within clearly stated sensitivity limits is a major contribution. It refines theory, informs future experiments, and preserves scientific resources for more promising directions. The emphasis on transparency means that whether the outcome is a discovery or a null, the community benefits. Now a few words about the quantum hardware in plain English. The Willow processor and similar devices operate by encoding data into quantum states and then performing transformations that reveal relationships classical codes might hide. In our context, the quantum kernel takes many pixelated lens images and embeds them into a mathematical space where small, consistent deviations become easier to separate from random noise. This is not a magical shortcut to truth. It is an engineered feature extraction strategy designed to prioritize promising patterns for careful classical follow-up. Operationally, the quantum stage functions like a highly efficient triage unit. It flags images where the compressed representation shows anomalous structure across many lenses. Each flag then triggers a battery of classical analysis. Refined mass modeling, spectral checks to confirm lens and source redshifts, PSF systematics tests, and synthetic injection recovery. Only after passing these classical gates would a candidate be promoted for cross-mission comparison between Webb and Euclid, followed by independent replication. Imagine the workflow as a layered security system. The quantum layer scans quickly and broadly, the classical layer investigates deeply and precisely, the cross-mission layer verifies independence, and the community layer reproduces or falsifies the final claim. No single layer is sufficient. Together they form a chain that makes false positives exponentially harder to sustain. What about timescales? Quantum triage can shorten the lead time from discovery to verification by prioritizing a manageable set of high-value candidates from an ocean of images. But the most convincing claims will still require months of classical modeling, instrument simulations, and independent replication. Science rarely accepts breathtaking claims without thorough, repeated checks. How should interested observers judge progress? Look for transparency milestones, preregistered test plans, public code with frozen commits, and independent teams publishing replication attempts. When the community can run the same scripts on the same data and reach the same score, that's when confidence grows. Avoid sensational headlines that appear before these milestones are met. The responsible path is incremental proof, not dramatic proclamation. Finally, think about the broader scientific value. This program sharpens tools used across cosmology: better lens modeling, improved PSF characterization, and more robust statistical practices. Those improvements uplift many other research areas: dark matter mapping, galaxy evolution, and precision cosmology, regardless of whether an extra dimension is found. In that way, the search pays dividends even if it ends in a null result. So to restate plainly, a quantum-assisted, population-level search for extra-dimensional leakage in gravitational lensing is a carefully constrained and testable program. It demands blinding, synthetic stress tests, cross-mission replication, and complete openness. It leverages the complementary strengths of the James Webb Space Telescope and Euclid, and it uses quantum processors as a focused triage tool, not a replacement for classical rigor. The next few years will tell us whether the cosmos hides a hidden hallway in the fabric of space or if 3 dimensions remain stubbornly complete. Stay ready. When the population score posts, the data, code, and analysis will be public for inspection for everyone.